Hello everyone, welcome to a class on basic electronic circuits. The topic for today is Zener diode as voltage regulator. In the analysis of Zener regulator circuit, Zener will be considered a non-state when it is reverse bias and the voltage drop across Zener is equal to or greater than its breakdown voltage. Otherwise, it will be considered to be an off-state. Zener regulator forms the last block in the power supply module as shown in the figure. It helps us to reduce the ripples or distortion in the output received from the filter circuit. This is the circuit of a shunt regulator where Zener is connected in shunt with the input source. The cathode of the Zener is connected to the positive plate of the battery and anode of the Zener is connected to the negative plate of the battery, making sure that the Zener is in the reverse condition. Since the Zener is reverse bias, you can replace it by an open circuit and you can find out the voltage drop across the Zener by using a voltage divider rule, and therefore we can write voltage drop across Zener V is equal to nothing but voltage drop across the shunt resistance or load resistance RL, which can be written as RL into Vin upon RS plus RL. Now, once this voltage across Zener, which is V, is greater than Vz, we can say the Zener has turned on and operates in the Zener region. Now, voltage drop across the load resistance VL will be equal to Vz. The circuit shown here is an equivalent circuit where the Zener is replaced by a battery with potential Vz. Now, let's start off with finding out various parameters of the circuit. Let's start with the current IRS. So the current flowing through the series resistance RS can be found out as the addition of current flowing through Zener plus the current flowing through the load resistance. The current flowing through the Zener can be found out to be a difference between the current flowing through the series resistance and the load resistance. The load resistance current can also be found out if you know the voltage drop across the load resistance. You can simply divide the voltage drop across the load resistance by RL using the Ohm's law. And you can also find out the current flowing through RS in the similar fashion using the Ohm's law. VRS can also be found out if you know V in and voltage drop across the load, because RS is connected between the load and the input. So IRS can also be written as V in minus VL upon RS. Power dissipated in the Zener is equal to voltage drop across Zener, which is Vz once it is on, into the Iz, that is nothing but current flowing through the Zener. Let's look into a numerical based on the above concept. Here we are supposed to determine voltage drop across the load resistance, series resistance and Zener, along with the current flowing through the Zener and power dissipated in Zener. We are supposed to do this for two values of load resistance, one 1.2K and the other being 3K. Let's start with the solution part A, where load resistance is equal to 1.2K ohms. First, we will be finding out voltage drop across the load resistance using the voltage divider rule. Therefore, VL would be equal to RL into Vin upon RS plus RL, which comes out to be 8.73 volts. Now, we will observe that this 8.73 volts is less than the Zener voltage, which is 10 volts. Hence, the Zener would be considered off. Since Zener is off, current flowing through Zener would be equal to 0 amperes and power dissipated in Zener would be 0 watts. Voltage drop across series resistance can be found out as difference between input voltage and load voltage. It comes to be 7.27 volts. Next, let's start with the part B of the numerical, where my load resistance is now equal to 3K. So we'll again start off with first calculating the voltage drop across the load resistance by using voltage divider rule. When RL is equal to 3K, voltage drop across the load resistance comes out to be 12 volts. Now this 12 volts is greater than the Zener drop, which is 10 volts, and hence we'll say Zener is on. And now we'll consider voltage drop across the load equal to the voltage drop across Zener, which is equal to 10 volts. Next, we can start off with calculating the load current and the series current by using Ohm's law. They come out to be 3.33 milliamperes and 6 milliamperes respectively. Next, we can find out Zener current to be a difference between the series resistance and the load resistance current, which comes out to be 2.6 milliamperes. Lastly, we can find out the power dissipated by the Zener to be Vz into Iz, which comes out to be 26.7 milliwatts. The Zener will act as a voltage regulator provided the input and the load resistance fall in a particular range. Let's first begin with finding out the range of RL for which the Zener will act as a voltage regulator. This can be simply done by finding out the voltage drop across load, which is equal to voltage drop across Zener, which can be found out using the voltage divider rule, which says RL into Vin upon Rs plus RL. By rearranging this equation, we'll be able to find out RL min, which is equal to Rs into Vz upon Vi minus Vz. And the maximum load current would be corresponding to the value of RL min. Once the Zener is in the on state, we can also find out the other parameters of the circuit. To find out the maximum resistance allowed in a Zener regulator, we'll have to refer to the maximum current that flows through the Zener, which is mentioned in the data sheet as IZM quantity. This IZM helps you to find out the minimum load current that flows through the load. Once you found out IL min, you can find out RL max using the Ohm's equation as shown. Let's look into a numerical where you to find out the allowable range of load resistance for the circuit to act as a Zener regulator. The values given are the maximum current flowing through the Zener is equal to 32 milliamperes. Vz, which is Zener breakdown voltage, is equal to 10 volts. Series resistance is 1 kilo ohms and input voltage that is to be regulated is 50 volts. Let's start with the solution. We know when the Zener is on, the voltage drop across the load or the Zener can be written as RL into Vin upon R plus RL. This will help us to find out RL min because we've already known the value of Vz. So RL min comes out to be 250 ohms. Next, let's find out the voltage drop across the series resistance, which is nothing but difference between the input voltage and the Zener drop, and hence it comes out to be 40 volts. Now using Ohm's law, we can also find out current flowing through the series resistance, and it comes out to be 40 milliamperes. Now you can find out IL min with the help of the current flowing through the series resistance and the maximum current that is allowed to flow through Zener. IL min comes out to be 8 milliamperes. With the help of IL min, now you can find out RL max, which is equal to Vz upon IL min. Lastly, we can find out the power dissipated by the Zener, which is equal to the voltage drop across Zener into the maximum current that is allowed to flow through the Zener, and hence maximum power dissipated across Zener comes out to be 320 milliwatts. We are aware that the voltage drop across Zener is also dependent on the value of Vin. We need to find out the minimum and maximum value of Vin for which the Zener will be on. We know voltage drop across the load or the Zener can be written as RL into Vin upon R plus RL. Rearranging this equation for Vin helps us to find out Vin min, which is equal to RL plus R into Vz upon RL. Maximum value of Vin is limited by the maximum current that flows through the Zener. IZM can be written to be IRS minus IL. and we can hence find out current flowing through the series resistance to be equal to IZM plus IL. Now since RL is fixed and IL is also fixed at Vz by RL, we can find out V in max to be equal to voltage drop across Rs, which is equal to IRs max into Rs plus Zener voltage. Let's look into a numerical based on the above concept. Here we are supposed to find out the range of input voltage for which the Zener will remain in the on state. Let's look into the solution. V in min can be found out to be equal to load resistance plus series resistance into Zener drop upon RL, which comes out to be 23.67 volts. We can find out load current to be equal to voltage drop across the load, that is Zener voltage, upon the load resistance, which comes out to be 16.67 milliamperes. The maximum current flowing through the series resistance can be found out to be equal to maximum allowable current through Zener plus load current, which comes out to be 76.67 milliamperes. The maximum input voltage that is allowed is going to be equal to maximum voltage drop across the series resistance plus Zener drop, which comes out to be 36.87 volts. Thank you.